to the Mind Grid, and today we are talking about fixed point math, an efficient alternative to floating point. So, with that, let's look at the introduction. Why fixed point math, and what is the context in which we exist today? So, I would look at two specific examples. One is our gaming consoles, and the gaming consoles started in the year 1972. You're probably aware of lots of different gaming consoles, starting with Ataris, then Nintendos, Segas, Super Nintendos, PlayStations, all the way up to the year 1996 when Nintendo 64 or N64 came out. The nice thing was that all the way up to this point, every game that you see here built on these earlier, consoles from 2600 all the way up to PlayStation, these did not have floating point units in them. So all the calculations were done using fixed point operations and fixed point math, integer math. I shouldn't say integer math, but it was all based on the fixed point math. Now, even things in complex computations like 3D graphics, all that had to do the fixed point operators. Now, if you look on the CPU side, you see 8085 coming out in 1976. Then you have the 80286 in 1985. You have the 80386 in 1985, or rather, the 286 was 82 to 85. But all these chips that you see here all needed a math coprocessor because they did not have a floating point unit inside of them. So they had their paired math processors because there was a cost associated with the floating point unit. So it was not embedded inside these chips, it was separate. It's only if you needed to. So now imagine programmers world that we had to develop code to assume whether it's going to be for the floating point unit or without the floating point unit with maybe some emulation, and the code quality would depend on the programmer's ability to use uh, the floating point unit or write code for without the floating point unit. Eventually, in the year 1989, 80486 came around, and this processor had the capability to um, to have the floating point unit inside. Right. So by this time, the solution had arrived, and at this point, you could write code to target the floating point unit. It'd be more accurate, at the same time, fast and efficient using that internal unit. Right. So now let's given the background of how things were done now, as a user of this binary math, if you start looking at the representation of numbers so that you can use these fixed point numbers in your own program, in your own chip or an FPGA, how does this number system actually work? So let's gain some insight into how the binary numbers actually work. And the first thing that we would look at is, we're not going to look at a 16-bit, 32-bit, 64-bit. They're pretty large numbers. Let's just take a very, very simple example. It's a 5-bit number. And the 5-bit number goes from 0 to 31, and then it wraps, goes back to 0, right? Very simple. But from this, I'm not a polymath. I'm not a, person who is really good at math. So I would say the first thing to my mind is if somebody asks me, okay, how would you arrange these numbers so that it makes computer sense? I would actually have no clues how to deal with this. But um, one thing that I can do, which is what I've tried to do here, is let's say I know where my zero is, right? Zero is very important because it centers you. So let's put the zero in the middle, right? And then what I can do is I can put the positive numbers, but positive numbers up to what point? So I don't know. I mean, at this point, positive numbers could be all the way up to 31. So you could put all the numbers on the right side of the number line, nothing on the left side. Uh, but if you're trying to represent negative numbers, so you know that half of your numbers have to be positive, the other half have to be negative. So I could throw all the numbers from 16 to 31, let's say, on the left-hand side, and 0 to 15 on the right-hand side, or 0 is in the middle, so 1 through 50 on the right-hand side. So now I know at least these numbers. I still don't know how to arrange them to make computer sense. So one other thing I can learn is that if you go from 0 backwards, the number that comes in computer sense is 31, right? It's not 16, it's not anything else. It's 31. If you go forward, it's 1. If you go backward, it's 31. So let's start putting those numbers like that. So on the left of 0, we'll put 31. Left of 31, we'll put 30, and so on all the way up to 16. So this now becomes some sort of a reasonable number line that I think the computer should like, right? So we can make use of this property that these numbers naturally, if you subtract or add 1 to these extent numbers like 31, if you add 1, it becomes a 0 because there's an overflow. Or if you subtract 1 from 0, you get a 31 because that's what happens in a very simple non-signed math. So just using very simple math here, I'm just going to do that. So now, taking all this into account, what I can do is that I can arrange these numbers on this donut or this circle. And I've just taken the same numbers that go from 0 to 31, and I've arranged them in this way that you have 0 through 15 on this right side, which I show as green. 16 should really be on the left side, and that's why I've shown in red color. But 16 should be on the other side of the spectrum because I think it's a negative number. But we will try to apply what we had learned in the previous slide that if you go left of 0, that is, we start subtracting, because we made it a circle, all the numbers were written in a circle. Uh, if you subtract 1 from 0, we know that it wraps to 31, and then 30, and so on and so forth, all the way up to 16 and 15, and so on and so forth. So these numbers make sense. Now we do not have uh, a cliff anywhere. Numbers are nice and even. If you can go forward, you can go backwards, everything makes sense, right? But what is the sense? What is negative? What is negative of 1, right? What is the negative of 2? What is the negative of 3? What sense does it have? We have these numbers arranged pretty nicely, right? But the way I think about numbers is that when I'm at 0, what does plus 1 mean? Plus 1 really means nothing till I say plus 1 is really if I go one click to the right of the number line, the thing that I meet is a plus 1. If I go one click to the left, the number that I meet is a minus 1. So if I apply this logic, very simple logic, and that's why I feel like 0 is the most important thing because it's defining where I am, right? If I don't know where I am, then I cannot go forwards or backwards. So let's say I'm at 0. And if I go forward by one click, I get a plus 1. Now, in this number system that I have now here designed, I call it my donut system. In this donut system, I can see that 31 was before 0. But I also know that if I subtract 1 from 0, I arrive at minus 1. So with that intuition, I can say that the that the number 31 is really a minus 1, right? This I'm making a connection here. And then same thing here, the number 30 is going to be a minus 2, and so on and so forth till you get to till you get to the number 17, and the number 17 is minus 15. The number 16 is minus 16. And that is it. This is the end of it. Because we said up to half of the numbers were on the positive side. So this is plus 15, right? Which you can almost call the end of the line. So it's your infinity or plus infinity. And the minus 16 is your end of the line on the negative side, which is minus infinity. So that is the intuition. The number system that this donut system, the way it works is that you start at 0 and you know that the max number in your number system is going to be on your left and the 1, 2, 3, and so on will be on your right, right? So now the next thing is the equivalence of negative and positive or subtraction and addition. So another way to think about the negative numbers now here is that when we look at negative numbers, let's say minus 2, right? So minus 2, when you are at some place, right? Let's say you are at 2. And if I say 2 minus 2, so some number minus 2 means I'm going to go 2 clicks to the left, right? So I'm going to go here. So I'm at 0, right? But going left by 2 is what if you go on the right by? right? Good question. So we know this whole circle is 32 clicks. If I went left 2 clicks, what is the complement of 2 clicks? It'll be 32 minus 2 or 30. So 30 would be, if I took 30 steps forward, that would be the same as 2 steps backwards. I would end up at this exact same position. And that is the equivalence of the negative and the positive. To convert a negative, which is going left by a certain amount, to a positive, which is going right by a certain amount or clockwise by that amount, we can convert subtraction to addition. So if you wrote minus 2, it could be written in a different way so that we never have to subtract. This minus 2 really is uh, a plus of 30, right? And that is minus 2. Because minus 2 was left, and let's say we never go minus, all we do is go right. So even to go left, we have to go right, right? So if we convert this to this, then that is the number system. So we have now arrived at 2's complement math, right? Because we do 2 power n minus some number k, and that, like I said, minus 2 is similar to plus 30, and minus k is similar to 2 power n minus k. So interestingly, um, what we have arrived at is that we have figured out how to convert all the negative numbers, right, into its equivalent positive number. And these numbers, now we can always go right. We do not like going left, so we're just going to go right from everywhere, because whatever the steps are to go left, we're going to convert it to go right, and then we're just going to keep adding and keep going right, and that is all we have to do. So now we understand that there is this number system and why it has 31 to the left of 0, right? In our number system, 31 is to the left of 0. The other thing is that these numbers have a certain equivalence. So if 2 is here, minus 2 is here, right? And just by a layman's analogy, I could think that maybe this would be minus 1, this would be minus 2. What about some other fancy numbers, right? So if somebody gives you 2000 something, how do you come up with that number? So the way you come up with that number is this 2 power n minus k. And another way to compute this 2 power n minus k, if you're given, let's say, some number 0, 1, 1, 0, um, you know, and if somebody says, or let's say, because you're talking 5-bit numbers, let's just say 0. So this is like 1, 2, 1, 2, 4. So this is 6, right? So if somebody says, what is minus 6? So what you can do is you can either do 32 minus 6, right? Which is, 26. Or the other way you can do is that you can invert every bit here. So 1, 1, 0, 0, 1, and then plus 1. So it becomes 1, 1, 0, 1, 0, right? So 1, 2, 4, 8, 16, right? So 16 to 18, 18 plus 8, 26. So that's the same thing. Either you can do it this way, 2 power n minus k, which is here. Another way to do this is just take 1's complement of a number and then add a 1. These are the same things, but the intuition behind this is that the equivalence of negative numbers to positive numbers comes from going right. We are, a race car driver. We only want to go right. We don't want to go left. Even if you want to go left, we don't go right to go left. So if you use that, all the negative numbers that occur on this side really are very large positive numbers. And that is the introduction. So now that we have understood why the numbers are done a certain way, now we're going to slowly migrate into how we will represent these numbers and how we represent like fractions and so on and so forth. So see you in the next section.